Hello physics students, Dr. Brenzi here. Our objective in this lesson, 5.1.2, is that we're going to be able to identify forces that cause centripetal acceleration and use this information to solve circular motion problems. I want you to think about this. Yesterday, or in a previous lesson, we talked about centripetal acceleration. In other words, an acceleration that is directed toward the center of a circle. According to Newton's first law, how can an object's velocity be changed? Well, according to Newton's first law, for every, I almost said Newton's third law. An object in motion tends to stay in motion unless acted upon by an external force. So there needs to be some force being exerted on our ball going around in a circle in order for this circular motion to even exist. So what force is causing that? And that's going to be the subject of today's lesson. It's centripetal force. Now, I have to warn you, centripetal force is not its own force. What I mean by that is, like if I'm listing types of forces that I'm familiar with, like gravity or friction or tension or drag force, I can't add centripetal force to that list. It's not its own force. What centripetal force is it's actually the net force of other forces that points toward the center of the circle. So we can have several forces acting on an object, add up all of those forces, and then the net result of that addition will be a force, a net force pointing toward the center of the circle. Now, when that net force points directly to the center of the circle, we have uniform circular motion. And the key word here is uniform. Okay, so in this figure, we are actually looking at the circle from the side view. And I'm going to ask myself, let's draw a free body diagram and see what forces are acting on this rock. We have the force due to gravity, which is pulling downward on the rock. And then we have the normal force, which is preventing the rock from continuing to fall. And then here, if the object is in motion, then we actually have a tension force exerted by the string. So we have tension force, we have a normal force, and we have a gravitational force. So if I want to find the net force, I'm going to add all these up. I know that normal force is going to balance out with gravitational force. So my net force that results is going to be a net force in this direction. And all of that is due to my tension force. So in a sense, my tension force is the centripetal force, the net force that is pointing toward the center of the circle. And it's always pointing toward the center because as this circle moves to a different, or as this rock moves to a different position on the circle, the tension force will be pointing toward this post on the left. Now, there can be cases when net force doesn't point directly at the center. And if that's true, then we don't have uniform circular motion. But there are moments where we can have circular motion. It's just that the angular velocity or the linear velocity is changing over time. Here might be a case where we actually have non-uniform circular motion. We have a wall on the left-hand side, and we have a string attached to that wall. And on that string is tied a rock. And this rock is actually moving in this direction right here. So we have a tension force moving in this direction. And the other force that we have acting on it is gravity. So there are only two forces acting on this rock right now. And what that means is that the net force is going to be the vector sum of these two, and it's going to point probably in a direction like that. Now, the exact direction it is going to point in really depends on how fast this rock is going around this circle. But for the sake of this particular diagram, the point I want to make is that there's a component of this net force that points in toward the center, but there's also a component of this net force that is actually tangential to the circle. So what's going to happen is that this part of the force, the net force, which happens to be the tension force, is going to be our centripetal force, which is going to cause circular motion. But because we have a force that is tangential, we no longer have a constant linear velocity. In other words, v is not constant around the circle. So this rock is actually, when it's moving in the downward direction, is actually speeding up due to the gravity. So that's why we don't have circular motion in this case. But we don't have uniform circular motion in this case. But we do have circular motion. So I want you to go ahead and practice on a piece of paper. Draw a free body diagram for each of these two scenarios. Identify the direction of the net force and ask yourself, will this result in uniform circular motion? Okay, I'm going to assume that you paused the video. And let's talk about the forces that are acting on this object to the left. What it is it's a disk. And the rock is on this disk, and this disk is, we're going to assume, is rotating around in a circle. So we have normal force, we have gravitational force. We know that on a horizontal surface, those are going to balance out. And we actually have a friction force. You might not have been able to figure that one out. But the friction force of the rock on the surface of the disk is actually what is giving us our centripetal force. You might be asking yourself, wait a minute, Dr. Brenzi, I know that friction force acts against the direction of motion or attempted direction of motion. I don't see this rock trying to actually move toward the center of the circle. What's going on here? Well, let's take a top-down view of this. So let's change our vantage point so that we're looking from the top down. And we have a rock over here. And this rock wants to move, according to Newton's first law, it wants to move in this direction. And it's going to move in that direction unless it's acted upon by an external force. The thing, though, is that the circle, the disk, after a short moment of time, is actually going to have a velocity that is going to change just the slightest bit from the rock's velocity. So if we are somebody who is sitting on this disk and we're firmly planted on it, what we're going to see as we start to continue to turn, we're actually going to see this rock move away from the center of our circle. It's hard to illustrate with just still pictures, but you can see that as I continue to go in this direction, and remember, I'm a person on the disk, I'm going to see this rock actually moving farther and farther away from the center. So if you're on the disk, you're going to see the motion working away from the center, and so friction is going to act counter to that motion, and it is going to actually produce a friction force that points toward the center of the circle. Okay. And that's all because there's a slight difference between the velocity of the disk and the velocity of the rock. Okay, in this one, on the right, you probably drew that there's a tension force. I gotta get the right colors here. Tension force along the string, right? And then there's a gravitational force. Okay. And you might be asking yourself, okay, well, what is my net force? If I add these two vectors together, I would get something that goes like this. And I'm asking myself, Dr. Brenzi, does that have any sort of component that is going toward the center of the circle? And actually, I fumbled this one up in AP class for a little bit until I realized that this tension force actually doesn't necessarily need to be equal to the gravitational force. As a matter of fact, it can be actually a lot larger. So if I were to draw a tension force, if this rock is going fast enough, this tension force is going to actually be quite large. And if I can find my eraser here, that's not my eraser. There's my eraser. I can actually make this tension force a lot larger. The faster this goes, the larger the tension force is going to take place. So if I have a large tension force, oops, all sorts of crazy things are happening here. So if I have a large tension force, what's that going to do to my net force? Well, now I have to change my net force, because now it is going more in a direction like that. Okay? And because it's now going more in a direction like this, there is a component of this net force that points toward the center of the circle. So it's going to be circular motion, but since it's not pointing directly to the center, it's going to be non-uniform circular motion. In other words, the linear velocity of this rock is going to be speeding up if it's going in this direction. As opposed to this picture where we have uniform circular motion because our friction force is actually pointing directly to the center of the circle. We can actually calculate how much centripetal force we need to keep an object on a circular path. Actually, this should say uniform circular path. So let me change that. Uniform. And the amount of force we need is Fc, centripetal force, is equal to the mass of the object times the centripetal acceleration. And we know from our last lesson that centripetal acceleration equals v squared divided by r. So you could use Fc equals mv squared divided by r. That would give you the centripetal force you need to keep an object on a uniform circular path. Now, those of you in AP, you can change this. Instead of using linear speed, you can involve angular speed, and the way you do that is you're going to replace v with omega times r. And when you do that, you're going to get m omega squared r squared, all of that divided by r, and then this r divides with one of those r's. And so we're left with m omega squared r. So that's just for you AP people. Advanced physics, you won't be responsible for that, or for knowing it, but, so I'll put AP only here. All right. Okay, so let me go through a couple of examples here. So we have a sled with a mass of 25 kilograms, and it rests on a horizontal sheet of essentially frictionless ice. It's going to be attached by a 5-meter rope to a post set on the ice. Once given a push, the sled revolves uniformly in a circle around the post. If the sled travels at 2.62 meters per second, find the force F exerted on it by the rope. Okay, so as I read through this, I notice I have a sled with a mass of 25 kilograms. So I'm going to come over here to a blank piece of paper, and I have a sled of 25 kilograms. Actually, I'm going to put that on the other side. 25 kilograms. Okay. And it says it is attached to a post. Oops. And let's see here, I've already forgotten what it is. Let's see, I'll have to go back here. Hold on a second. It's attached by a 5-meter rope to a post set on the ice. Oh my goodness, sorry about that. There we go. And then it says it revolves uniformly in a circle at 2.62 meters per second. Okay, so let me go back to my drawing here. Whoa, how'd that happen? Okay, so radius is 5 meters, and it is revolving at 2.62 meters per second. So this sled, excuse me, is going to go around in a circle. This is a bad-looking circle. All right. So that's the path that our sled is going to make. And we want to know what force is required in order to achieve this uniform circular motion. So let's use our centripetal force equation, Fc equals mv squared divided by r. The mass is 25 kilograms. The velocity is 2.62, so I'm going to square that. And then divide it by the radius, which is 5. And I'm going to end up with 5. I take 25 divided by 5. That's 5 times 2.62 squared. And let's see, 2.6 squared, that's going to be about 6 points. Let's say about 6.3. Let's see, is that going to be right? Yeah, let's say 6.3. I'm doing mental math here. You might get a different number in your calculator. But anyway, if I take 5 times 6.3, I get something around 31.5. Yeah, 31.5 newtons. All right. Now you might come up with a different number, but you come up with a different number only because I'm using mental math, because I'm too lazy to grab my calculator right now. All right, so that would be the centripetal force that would be required to make this uniform circular motion. Whoa, and something happened to my slides here. There we go, that's better. Okay. Now a slightly more complicated example. Actually, I'm going to pause the video for a moment on my side. You'll actually hear my voice here in a moment, but I'm going to pause it here because I have something that I need to quickly do. So I'll do that and then I'll come back here in a moment. Okay, so let's go through this second example here. So we have a 20-gram penny that's placed on an 0.8 meter diameter table undergoing circular motion. The penny is placed 0.25 meters from the center. If the coefficient of friction between the penny and the turntable is 0.30, calculate the maximum tangential speed the penny can have and still remain in circular motion. Now, this word tangential might be unfamiliar to you, but what does it look like? It looks like the word tangent. So, if we have something in circular motion, the velocity of an object going through circular motion is going to be tangential to the circle itself. So, even though in the problem it's called tangential speed, we've been calling it linear speed. So, it's basically asking us to find the linear speed of this penny, or actually the maximum linear speed of this penny. All right. So we have a circle or circular table, and it has a diameter of 0.8 meters. So be very careful about when you read word problems what it exactly is giving you. So if the diameter is 0.8 meters, that means the radius is 0.4 meters. And it says if a penny is placed 0.25 meters from the center, so the penny's not placed all the way at the end or the edge of the table. I'm just going to write 0.25 meters here. There we go. Okay, so that's how far that penny is placed from the center of the circle. And I need to ask it actually also gave me the coefficient of kinetic friction, which is 0.30, or actually the coefficient of static friction. So the coefficient of static friction is 0.30. How fast can this penny go around the circle before it starts to slip? That's what we want to know. All right, well, I have a formula for force, centripetal force, equals mv squared over r. Okay. Now the thing that's supplying my centripetal force is the force due to friction. So let's replace Fc with F sub f. Okay, and that's going to equal mv squared over r. Well, what is the force due to friction? That is equal to the coefficient of friction times the normal force. And in this case, the normal force is balancing the force due to gravity. Because we're on a horizontal surface, we're not applying any extra force in the downward or upward direction, so we can set normal force equal to mg. And on the other side, we have m times v squared divided by r. All right. Now, we could plug in numbers at this point, but I noticed right away that I have a factor of m on this side and I have a factor of m on that side. So if I were to divide both sides by m, those factors would drop out. So I'm going to save myself a little bit of number crunching work. Now let's go ahead and start filling in what other things we know. So we know that this is 0.30, the coefficient of friction. We know that g is equal to 9.8. And then we have to set that equal to v squared, which is what I want to find out, divided by r. Now be very careful about which r you use here, because we have the radius of the table, but we also have a distance from the center out to the penny. Which radius should I put in here? Well, I'm concerned about the maximum speed of the penny, so I better use the penny's position, or the penny's radius, as the value of r I enter into here, so I am going to actually have to use 0.25. All right, well, let's multiply both sides of this equation by 0.25 to get v squared by itself. And when I do that, it looks like I'm going to get something close to 0.75 on this side. It might be 0.74 or so. Again, I'm doing some mental math in here. And if I take the square root of v squared, I get a number, if I remember right, approximately equal to 0.87 meters per second, somewhere around there. Okay. So, that is the maximum linear velocity or tangential velocity that this penny can go before it starts to slip off of our table. So if this velocity is any faster than 0.87 meters per second, then penny goes, whoop, slides off. Okay. All right, ladies and gentlemen, that is it for this video. I hope you have a good day, and I look forward to seeing you soon. Bye.